So for part one, we're going to be using Raoult's law to derive equations for bubble and dew point for ideal solutions with two components. So to start off with Raoult's law, we have the mole fraction in the liquid phase of component I multiplied by pressure of saturation of that component, um, and that is equal to the mole fraction in the gaseous phase multiplied by the total pressure. And we use this equation to solve for the bubble and dew point temperatures by using the pressure of saturation of the vapor, which is reliant on the temperature. So to solve for um, or to derive the equations for bubble and dew point, we can first separate this equation out for multiple components. So if we have x1, pressure of saturation of component 1, is equal to y1p, and x2, pressure of saturation component 2 times y2 times pressure. And we can add these two together to get um, an equation that can solve for two different components at the same time. Okay, so then if we want to solve or derive an equation for bubble point, we can take this equation up here and we can rewrite it and simplify the right side by using the fact that y1 plus y2 is equal to 1. And this is because with mole fraction, the two different mole fractions of the different components is always going to be equal to 1. So then what we can do is we can rewrite the equation above. So x1 is ps1, x2, pressure of saturation of component 2, is equal to p, because y1 plus y2 is equal to 1. If we factor out the p, we can um, just get p times 1. And then from here, it is simpler to rewrite the equation as a summation of I, any number of components, and then the mole fraction of said component multiplied by that component's pressure of saturation. That is equal to the total pressure. And then if we want to um, derive an equation for dew point, um, it's actually easier to go back to the split equations here. So if you have x1 ps1 is equal to y1 p, and x2 ps2 is equal to y2 p. And then if we solve these equations for the mole fractions of in the liquid phase of component 1 and 2, we get x1 is equal to y1 times the pressure over pressure of saturation for component 1, and x2 is equal to y2 times the pressure over pressure of saturation for component 2. And then using the same um, equation as we did up here for mole fraction, that means that x1 plus, x2 is equal to 1. And then by adding these together, we can actually rewrite it in the form of a summation again, using I, that the vapor mole fraction of component I times the pressure over the um, pressure of saturation of component I, and the summation is going to be equal to 1. And using these in our code, we should be able to solve for the bubble and dew point temperatures and create plots that show that depending on the temperature, the bubble and dew point is going to be slightly different. That is due to the fact that the pressure of saturation of a given component in the vapor phase is different depending on the temperature.